Hello everyone. It is a great pleasure to share with you our study entitled Detection and Prediction of Epileptic Seizures Based on EEG and Deep Learning, a review. This presentation provides a comprehensive overview of recent advances in EEG-based seizure recognition and prediction, emphasizing the contribution of deep learning techniques to improving diagnostic efficiency and predictive accuracy. The talk is structured as follows. We begin with the background on epilepsy and EEG, followed by the motivation for automation, a review of related literature, an overview of model architectures, a comparative analysis, and finally, the conclusion and perspectives. Epilepsy represents a major neurological disorder, with the World Health Organization estimating approximately 65 million affected individuals globally. It occurs across all age groups, but is particularly frequent in infants and elderly populations. The recurrent seizures, which may involve involuntary movements and sudden loss of consciousness, can endanger patients' safety and considerably reduce their quality of life. Consequently, timely recognition and accurate diagnosis of epileptic episodes remains of a paramount importance. Electroencephalography, or EEG, is regarded as the gold standard for investigating cerebral electrical activity. It is extensively employed to clinical neurology for the recognition and classification of epileptic seizures. Nevertheless, the manual interpretation of EEG signals is highly demanding, requiring specialized expertise and considerable time, which can limit efficiency and consistency in clinical practices. The traditional manual inspection of EEG signals is not only time-intensive, but also susceptible to subjective interpretation. This raises the need for computational frameworks that can provide objective, reproducible, and efficient support to clinicians. Automated recognition and classification systems offer the potential to enhance diagnostic accuracy, reduce delays, and facilitate large-scale clinical applications. In light of this, artificial intelligence, and more specifically deep learning, has emerged as a particularly promising avenue. In this context, a review of literature studies on practical approaches to epileptic seizures recognition using deep learning was carried out. Our contribution collects recent articles in this field up to 2024 and highlights the most important findings to aid future research. In fact, we have carefully selected 43 publications relating to the detection and prediction of epileptic seizures based on EEG modalities and deep learning models. Based on a general architecture, as shown in this figure, the process involves the following steps. First, we collect the EEG signal data from the dataset. Then, we perform data pre-processing based on the removal of unwanted frequencies and segmentation into smaller parts for detailed analysis. Features are then extracted and classified by deep learning models. After signal transformation in the time frequency, or nonlinear domains. Finally, performance is evaluated using appropriate metrics. In current research, EEG data is primarily obtained from either intracranial or scalp recordings. Among the datasets employed for training and validating deep learning models for seizure recognition, the CHB-MIT dataset is the most widely used. Other frequently referenced datasets include BON and TU-HEEG. These datasets provides a standardized benchmark for developing and evaluating automated recognition and classification methods. Preprocessing is a crucial step before feature extraction and classification can be carried out effectively. The first step, filtering, aims to suppress noise and artifacts such as power line interference or muscle activity. For example, Butterworth bandpass filters are commonly applied to scalp and intracranial EEG. Resampling is another essential step. Although EEG is often acquired at high sampling rates to capture the temporal details, downsampling, such as reducing IEEG from 2048 Hz to 256 Hz, strikes a balance between information preservation and computational feasibility. Finally, segmentation breaks long EEG recordings into manageable epochs, which enables localized analysis and reduces complexity in subsequent processing. These pre-processing steps minimize interference and improve the quality and reliability of the data, thereby ensuring that downstream feature extraction and classification are both accurate and meaningful. Following pre-processing, EEG signals undergo feature extraction through multiple analytical domains, providing the foundation for robust recognition and classification of epileptic events. In the time domain, we directly examine EEG amplitude fluctuations to capture transient patterns, employing statistical descriptors and morphology-based features. The frequency domain allows spectral decomposition, enabling the characterization of brain rhythms. Techniques such as FFT and MFCC are routinely employed to extract relevant frequency-based features across delta, theta, alpha, beta, and gamma bands. Considering the non-stationary nature of EEG signals, time frequency representations such as STFT and CWT are particularly effective, preserving both temporal and spectral information simultaneously. Finally, nonlinear analysis model complex neuronal interactions that linear methods cannot capture. Approaches such as path signature, PCC, entropy-based measures, and EMD provide a rich, high-dimensional representation of EEG dynamics. In our study, we investigated several deep learning models for the detection and prediction of seizures. CNN models effectively extract local spatial features from the EEG spectrograms or scalograms, but they do not capture temporal dependencies. LSTM models capture short and long-term temporal patterns, but they lack spatial information. CNN LSTM models integrate spatial and local temporal modeling, improving performance for moderate length sequences. Transformer models utilize self-attention to efficiently capture long-range temporal dependencies, though local details may be underrepresented. CNN transformer and LSTM transformer models combine local modeling with global attention-based modeling for enhanced performance. Finally, the CNN LSTM transformer models provide a comprehensive framework capturing spatial, local temporal, and long-range temporal features, enabling robust and accurate seizure detection and prediction across long EEG sequences. In reviewing EEG-based seizure detection and prediction models, several research gaps were identified. Data-related issues include limited diversity of patients in current datasets, which can reduce generalizability. Expanding to multiple EEG datasets and including real-time recordings is essential to develop robust models that can work across different subjects. Model complexity is another challenge. While advanced architectures like CNN LSTM Transformer offer comprehensive feature learning, they increase computational demands and make training more difficult. Moreover, pre-processing pipelines may not fully handle noise artifacts or the redundant channels, potentially affecting model performance. Performance challenges remain in enhancing sensitivity and recognition accuracy. Many models are trained on individual patients, limiting their generalization to unseen patients, which is a key considering for a practical deployment. Application and deployments are also limited. Few models have been validated in real-time EEG scenarios or in wearable devices. Developing approaches that improve adaptability across different patients will be crucial for the transition from research to real-world application. So to conclude, EEG-based seizures detection and prediction has made remarkable strides thanks to deep learning. Today, we can capture complex patterns from brain signals that were once invisible to traditional methods. Yet, challenges remain. Current datasets are limited, models can be complex and resource demanding, and patient-specific variations still affect performance. Real-world applications, especially in real-time or on wearable devices, are just beginning to be explored. The exciting part is that solutions are within reach. By combining diverse EEG datasets, advanced reprocessing, and hybrid models that learn spatial, local, and global temporal patterns through attention mechanisms, we can move closer to robust patient-independent seizure prediction. Ultimately, this research is more than just algorithm. It's about improving patient care. The better we understand and model these signals, the sooner we can provide timely interventions and enhance the quality of life for individuals living with epilepsy. Thank you for your attention.